Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. In this session, we are going to study in detail the velocity and acceleration analysis of a slider crank mechanism with a example problem. This is an example problem of related to a slider crank mechanism. Let me read that. The crank of a slider crank mechanism rotates in clockwise direction at a constant speed of 300 rpm, revolutions per minute. The crank is 150 millimeter and the connecting rod, the length of the connecting rod is 600 millimeter. Determine objective 1, linear velocity and acceleration of the midpoint of the connecting rod, that is point D, and linear velocity and linear acceleration of the point D, that is the midpoint of the connecting rod AB. And objective number 2, angular velocity and acceleration of the connecting rod, angular velocity of the connecting rod and acceleration of the connecting rod at a crank angle of 45 degree from the IDC, inner dead center. Here OB is the crank in this figure and AB is the connecting rod and A is the slider, and D is located at the midpoint of the link AB, that is connecting rod AB. AB is the connecting rod. So this OB is rotating. What is the speed of the OB? The OB is rotating 300 rpm. That OB we are going to convert it into angular velocity of B with respect to O, that omega BO equal to 2 pi n by 60. 2 pi times n, 300 revolutions per minute by 60. That equal to 31.42 radians per second. And the length of the OB is given here, and the length of the connecting rod AB also given, and the location of the point D also given. The location of the point D is the midpoint of AB. The midpoint of AB, that is 300 millimeters at the point A or from point B. That is the midpoint. Now, what is omega BO? The omega BO is 2 pi n by 60. That is 2 pi times 300 by 60. That is 31.42 radians per second. That is OP equal to 150. That is 0.15 meters. And the length of BA, that is BA equal to 600 millimeter, convert into meters, that is 0.6 meters. And what about D? The D, either AD, that is equal to BD, that equal to 0.3 meters. That is the midpoint of connecting rod AB. So it is half of the distance of the length of the connecting rod AB. Now we know the linear velocity of B with respect to O, or velocity of B. Linear velocity of B are with respect to O, with respect to fixed link. That means it is absolute velocity, that is R, velocity of B. The velocity of B equal to VBO equal to we know linear velocity equal to R times omega, where omega BO, what is the R? R is the length of the link BO, that is OB times omega BO. Omega BO, angular velocity of the B is 31.42 radians per second, and the length of link OB equal to 0.15 meters. If you multiply, then the product comes. The product is observed as 4.713 meter per second. We know the value of velocity of B, that is 4.713 meters per second. Consider the scale in the vector scale, this velocity into the vector scale, that is 1 meter per second equal to 1 centimeter. Then 4.713 meter per second equal to how many centimeters? That equal to 4.713 centimeters will come. That is the vector O to B. So thus we have to take the required suitable scale and convert it to vector scale and draw the velocity diagram. Here the given diagram is a space diagram or configuration diagram. So we have to redraw the configuration diagram into your answer script in order to draw the velocity diagram and acceleration diagram. So let us begin. How to draw the velocity diagram or velocity polygon? First step. The step 1 is procedure. The procedure is draw vector OB. Draw vector OB perpendicular to the link BO. Capital letters indicates related to configuration diagram. To some suitable scale to represents the velocity of B with respect to O, or simply velocity of B, that is VBO. That is VB, such that the vector OB equal to 4.713 meters per second. Now here it is, let us see, start, that is OB. It represents velocity of B, which is normal to the link BO. Why it is normal? Because the path of any particle on the link, its velocity is normal, that is a tangential to the path, that is tangential to the rotation. Tangential to, that's why this in this VB denotes tangential to the particle, VB, the tangential. That is principle. Based on that principle, that's why all the velocity vectors are normal to the links in the configuration diagram. Okay. Now OB, that OB equal to, we have drawn OB, that is VB. That VB is normal. Yeah, that is OB vector. In this OB vector, the direction is known and velocity, the magnitude and direction both are known here. That's why we have drawn. It is in clockwise direction. That's why. If it is counterclockwise direction, it is opposite. In downward direction, it will come out. Okay. Next, point number 2. What is the step number 2? From point B of a vector diagram, draw A perpendicular to BA represents the velocity of A with respect to B. With this BA link, keep the protractor such a way that our minute drafter scale, if you keep the minute drafter scale one scale, another perpendicular, that perpendicular line you have to draw either upwards or downwards. And from point O, that is the second step, and from the point O we have to draw, because this slider, velocity of the slider is linear velocity. That's a parallel line you have to draw. Again, after that, from point O. To draw point O like that, again point B, then intersects. That is the point. Alright. So now, second step, that's what VAB. We have drawn the point. We have drawn the point from B to A. This BA line is normal to the link of the spatial diagram. You can use either set squares or you can use minute drafter in order to draw a perpendicular line to the space diagram. This space diagram we have to redraw from the question paper to your answer script. That is also part of velocity diagram, velocity analysis. So for velocity analysis, we need a space diagram and the required known values. We have to maintain it. Now, to the space diagram, link AB, you keep your minute drafter scale, one of the small scale, then larger scale indicates the perpendicular line. That perpendicular line you draw. Then it is the perpendicular to link BA. This link BA, we don't know the magnitude, but we know only direction. the direction, but what is the magnitude we don't know. Then third step is parallel to link A. If you draw, we have to draw what is the linear motion of the slider. The slider is linear motion. The velocity vector is parallel to the motion. So that line if you draw, this is the line, that is OA. That OA and BA intersects at point A. Alright. Now, if we measure this AB length, that AB gives the velocity of link AB, VAB. And the vector OA represents the velocity of A with respect to O. What is the velocity of A here? The velocity of A is the slider velocity. Thus, the slider velocity can be known, and also the velocity of the connecting rod can be known by using this, by drawing the velocity diagram. Alright, you measure this, that is velocity analysis. Now, how many links are there here in this slider crank mechanism? Fixed link O, OB is the crank, AB is the connecting rod, and A is the slider. OB, both magnitude and direction values are given. So what are the unknown values are? The unknown values are drawn or found by using the velocity diagram. The unknown values are what? Unknown links are unknown values of the links are connecting rod and slider. The connecting rod is AB and the slider is A. VA and VAB values are found by using this velocity diagram. Now, after calculating this, then we found that the velocity VAB equal to that is vector BA, that equal to convert into the required scale. Then the velocity of connecting rod is 3.4 meter per second is calculated. And the velocity of A, that is VA equal to vector OA, that vector OA equal to 4 meter per second. So these are the values of AB and A, 3.4 meter per second and 4 meters per second. Okay, that is the velocity diagram. Now we have to find out one more important. The important is that we need the velocity of the midpoint of D. How to get this midpoint of D? Very important. This midpoint of D, velocity of D with respect to O, we need. How to get it? We have to use the division formula, that is AB by AD or AD by AB. We have to use the BD by BA. You consider either AD by AB or BD by BA, that equal to vector of BD by BA. We have to use that is in the space diagram. In order to find out the midpoint of connecting rod, if we use this formula, this division rule, we can know the vector length of BD. Here it is midpoint. No need to use any formula directly. We can also use, there is a vector is there, BA, and that BA midpoint is the BD. You can mark directly with the same proportionality. It will follows from configuration diagram to vector diagram. We can follow the same thing, but if it is not midpoint, then what is the value of the BD? By using this division rule, we have to find out the length of the vector of point D on the connecting rod. So BD by BA equal to the space, that is BD by BA. We know that BD by BA, here it is midpoint, so you can mark directly. So after this, what we know, the BD values, that is the dimension of the link BD, and BA, that is also link. What is the BD value? Suppose BD by BA. What is the BD equal to 0.3 meters? It is 0.6 meters. That is 1 by 2. that BD equal to half of BA. Okay, that is midpoint, half of BA length, midpoint D. So join OD, O to D. Yes. Now the vector OD represents the velocity of the midpoint D of the connecting rod, that is VD, midpoint of the connecting rod. Then OD is the velocity of the midpoint of the connecting rod. By measuring this value, by measurement, we find that vector OD equal to how many meter per second? 4.1 meter per second. Thus, we have to find out the midpoint of D, velocity of the midpoint of the D on the connecting rod. That's what so far we covered, how to find out the velocity of midpoint of D on the connecting rod. And in order to find out the midpoint of D, we found the vector, that is the velocity of connecting rod AB, and the velocity of the slider A also in the previous slides. Now there is another objectives are given, the angular velocities components. What is the angular velocity of the component? Let me find out. Let us discuss. So we know that radial acceleration BO equal to, that is radial acceleration, that is AB, B equal to V square BO by OB, that is 4.713 whole square by 0.15, that is 148.1 meter per second square. And also we know certain radial components. What are radial components of connecting rod? The radial acceleration of the connecting rod, that is AR AB equal to V square AB by BA. V square VAB 3.4 meter per second whole square by 0.6, that is 19.3 meter per second square. Okay. Now very important is that a point at the end of a link which moves with constant angular velocity on a link, it has no component of tangential acceleration. Here the link OA having, it is moving with constant angular velocity. What is the constant angular velocity formula? Constant acceleration, that is tangential acceleration, is R times alpha. If it is constant angular velocity, then means what is the acceleration is 0. Then there is no AT, no tangential acceleration. Then what type of acceleration that link consists? That link consists of only radial acceleration. So that is the total acceleration. Next, when a point moves, suppose the link A, the slider A, it is moving what? Linear, okay? At that time, it has no moving along a straight line, Then what about radial component? The radial component is 0. That means AR, radial acceleration, is 0. No radial acceleration. Then what type of acceleration? It consists of only tangential acceleration. Then the total acceleration of a slider is tangential acceleration. Whereas for crank, where the crank is rotating with constant angular velocity, then there is no tangential. Then what is the total acceleration? That is radial acceleration. We have to understand these concepts. So what are the values we know? We have to known values. Based on the known measurements, we'll calculate manually the particular parameters or acceleration components and velocity components. By using those vectors, we'll draw. Then unknown vectors will come out. That is the concept. Now, that is VAB equal to vector BA and VA vector OA, that is 4 meter per second, we know. From in this, we found out radial, that is ARBO. That means ARBO is nothing but ABO, because there is no tangential component of acceleration. That is AB equal to 148.1 meter per second square. And AB radial component. But we need, what is our objective here? The objective is There are two objectives are there. The two objectives are, yes, we should not miss the two objectives. Acceleration of the midpoint of the connecting rod and also angular acceleration of the connecting rod. Okay. Angular acceleration of the connecting rod and acceleration of the midpoint of the connecting rod. Thus we have drawn. But we need acceleration components. But we found out radial and also a radial component, radial acceleration of crank. That is the total acceleration of the crank. And radial acceleration of connecting rod AB. Alright, that is 19.3 meter per second square. Now, how to draw the velocity acceleration diagram? We want midpoint of the connecting rod. That is point D. Acceleration of midpoint of connecting rod, that is point D. For that midpoint, what to do? We have to draw the acceleration diagram. Okay. How to draw the acceleration diagram? Let me read point number 1. We know the known value of link OB, the total acceleration, that is ARBO, that is ABO, that equal to 148.1 meter per second. So that is a radial. Draw a parallel line with the help of mini drafter or set squares to this configuration diagram and draw a line, that is A dash, any point A dash, sorry, O dash and A dash is there. Yes, O dash, A dash. Draw a line, but we know what is the point? OB dash, O dash, B dash. Draw a line AB of radial component of acceleration, that is called AB, with some suitable scale. This line is radial direction, that means parallel to the link of OB. Draw a line. That is the first step. Step 1. With known values, you can consider what is the known scale. Suppose 148.1 meter per second is there. You can consider 50 meter per second square equal to 1 centimeter vector scale. Then 148.1, it comes to 2.48 or 3 point. Okay. Closer to 3 centimeters comes. Draw a line. O dash B dash is 3 centimeters vector. Next step, point number 2. Next step is B dash, and if you want further, it is connected what? This AB is consists of, connecting rod is consists of two accelerations. What are they? One is radial component, another one is a tangential component. But we know the radial component value. What is ARAB value? That ARAB, that is 19.3 meter per second square. So draw a line 19.3 meter per second square, that is B dash X. ARAB we know. That is step number 2. After that, you draw a line that is normal to the radial acceleration component. We don't know the magnitude value of tangential component, but we know the direction of tangential component of acceleration of AB is normal to the radial component of acceleration. Draw a line, that is radial component of acceleration. Okay, this is the line you draw. That is ATAB, we don't know the magnitude. Next point, what is the third step? This is the third step. What is the fourth step? Now, this slider A is having which component? Tangential component. But we don't know the magnitude, but we know the direction. This tangential component, this slider A is moving tangential to with respect to fixed link. What is the fixed link is? Point O dash. O dash is the fixed link, that is the pole. From that, draw a line parallel to the motion. Draw a line parallel to the motion. Yes. This intersects at point, which point? A dash. Now, O A dash is the tangential component. Now, join this tangential and radial components. This is tangential radial components you join. Then that is the total acceleration. This is step 4. and it is the step 5. Then what is the vector? The point D. We want angular velocity or acceleration of the point D. How it comes to point D? Again, the division rule you follow. That is B dash D dash by B A dash B dash B dash D dash by B dash A dash equal to BD by BA. By using this division rule, then what to do? We will find out B dash D dash. But it is a midpoint of configuration diagram. Point D is on the midpoint of configuration diagram. Mark the point D on the this vector diagram and join O dash and D dash. Join O dash D dash, that point, step number 6. Now you know, you measure O dash D dash vector value. That vector value gives acceleration of the midpoint of D. And you measure this total acceleration. A dash B dash. A dash B dash vector gives acceleration of AB. Okay. O dash D dash vector gives acceleration of point D. O dash A dash vector gives acceleration of slider A. So you measure these vectors and convert to suitable scale, then we can find out the vectors, the accelerations of those links. Now, angular velocity of the connecting rod. What is the angular velocity of the connecting rod? That is omega AB equal to VAB by BA. What is the VAB? 3.4 meter per second by 0.6. That is 5.67 radians per second. Alright, next. Angular acceleration of the connecting rod. What is the angular acceleration of the connecting rod? This angular acceleration of the connecting rod values comes from, we can observe from where? That is from acceleration diagram. What is the angular from the acceleration diagram? What is the angular acceleration? That is ATAB, tangential. ATAB, that is, this is value A dash X. That is A dash X value. If you measure, that comes under 103 meter per second square. Now we want angular acceleration that equal to alpha AB. That is alpha AB equal to tangential AB by AB. We know that ATAB, that is 103 meter per second square, and AB length is 600 millimeters, that is 0.6 meters. That is 103 by 0.6. Then 171.67 radians per second square. So these are the two objectives we completed in this problem. By considering slider crank mechanism case, we found out both angular accelerations and angular velocities of the midpoint, both midpoint D and also links of connecting rod AB. Okay, that is the manner one has to solve. Okay, let me explain it. What is required, how to start this problem. Whenever this type of problem is given in the examination, what are the things we have to start? We have to do it. Whenever they will give problem with configuration diagram along with the dimensions of the various links, we have to redraw the configuration diagram into your answer script. That is your reference. That we have to exactly redraw by taking the scale, some reduction scale or maximization scale. Suppose 150 millimeter, that is the OB, that is 15 centimeters. The length of your answer script itself only 15 centimeters. It goes out. So what to do? You use the reduced scale. That is 10 millimeter equal to some by 2 scale. That is 7.75 millimeter. That is 7.5 centimeters. Make 1:1 half of the scale you consider. Then reduce proportionately. First to draw the configuration diagram. You draw the configuration diagram or space diagram. Here I mentioned as a space diagram. That is also known as configuration diagram. So you draw configuration diagram and also give the space of velocity and acceleration diagram should be beside the configuration diagram. So it can be easy for you to draw velocity vector lines and acceleration vector lines. The velocity vector lines are always normal to the configuration diagram links. Always. So that it should be beside, it should be convenient. Not you cannot draw space diagram at one corner and velocity diagram another corner. If you have enough size instruments, especially we need 2 set squares or 1 mini drafter. So if you have a mini drafter, you set the scale. Mini drafter is having large scale and small scale, no? You set parallel to this one of the configuration diagram link, automatically the large scale indicates normal line. That normal line you can draw. So this velocity diagram, in the velocity diagram, all vector lines are normal to the configuration diagram lines. Configuration are normal to the links of a configuration diagram. Okay, so that it is very, very important. You have to use this configuration space diagram should be, and velocity diagram should be the beside to space diagram. It is easy to draw. Now if you analysis this OA line, okay, let me start. O is connected to B. This OB line is normal to link OB, connecting space diagram line OB. And BA line, you see BA vector line, this BA vector line is normal to the link in the space diagram BA, AB, normal line, exactly it is normal. Next, what about the path of the slider? The slider is having a motion tangential, linear motion, that's why parallel line, only for slider parallel line comes. Remaining all vector lines are normal to the motion of the links, especially only for slider having a sliding motion. If the slider is perpendicular, it is moving, slider motion is, then you draw a line parallel to the slider motion, that vector line. So thus we'll draw even point D. The point D line, if you consider it, this is OD line is, OD vector is normal to the AB, that is D. Okay, we make it move. Now, next one. In the case of acceleration diagram, what we have done? In the case of acceleration diagram, if we consider here, if based on the data, if the crank is having constant angular velocity, if you know the concepts of what is radial acceleration and what is tangential acceleration, the radial acceleration is formalized v square by the length of the link, and tangential acceleration that equal to r times alpha. So it is OA, the crank is moving with constant angular velocity, that means alpha acceleration component AT is 0, that means only radial component. Then total acceleration equal to AR plus AT, then AT is 0, then it becomes only AR. So the total acceleration of the link OB is what? That is only radial acceleration. So based on the requirement, and if you consider the slider doesn't have radial acceleration because no rotation. What is their tangential component? So thus, what are the known values are there, we have to calculate and keep it aside. Then you join according to the whatever data is available, based on the data you draw a vectors, that is in acceleration. Now this AR means radial components are parallel to the links of a connecting rod. But slider, it is only tangential, means parallel line. But in the case of other links, AR is parallel to link OB. Again, for AB, there are two components are there. One is radial, another one is tangential. The radial is parallel to the configuration link AB, and tangential is normal to the link AB. Now here, the portion O dash B dash, total acceleration is radial acceleration. So this O dash B dash vector is parallel to the configuration link OB. Next, this AR AB is parallel to the link AB. It is also parallel to link AB. But AT is perpendicular to link AB, connecting rod. Link AB is the connecting rod. The next, O dash A is moving only tangential. That is a parallel. There is no radial component. You draw. This is a parallel line to the sliding motion. The intersection point is A dash. Alright. Next, if you join it, these two, that is the total acceleration. The total acceleration. So this total acceleration is the sum of the vector again, triangular forces. Triangular we have used here. AR, AT, join here. Then the point D, that is AD acceleration. This AD acceleration consists of both what? This is the total acceleration of the midpoint of D. Thus, we have to find out, we have to draw the velocity diagram, acceleration diagram and space diagram. And one more thing, finally conclusion is that velocity and acceleration diagrams are dependent on space diagram. And velocity diagram is dependent on space diagram. And acceleration diagram is dependent on velocity diagram. So, and that you make a plan of your answer script such a way that the space diagram, velocity diagram and acceleration diagrams these three are beside each other. Then you can draw easily. Okay, that is very important. That's if you want it directly, if they ask you in examination, find the angular acceleration of link AB. They did not ask you about velocities of different links. They asked those acceleration components. That means we have to draw configuration diagram. We have to draw velocity diagram. From velocity diagram, acceleration values can be found. Suppose if they asked you only in examination velocity components of various links, then we have to draw only two diagrams. Number one, configuration diagram, two, velocity diagram. We can no need to draw acceleration because acceleration diagrams, acceleration objectives are not asked related to acceleration values. So if they ask velocity only means configuration diagram is must and should to draw the velocity diagram. And configuration diagram and velocity diagrams both are must and should for drawing the velocity diagram. Okay. With this, we stop this session. Very, very important model for end examinations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.